Hi guys, let's do maximum depth of a binary tree. So we're given the root of a binary tree and they want us to return its maximum depth. And they tell us that a binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So in example 1, we're given this tree where we output 3 because the maximum depth is 3 if we take the path of node 3 to node 20 to node 7. That has a depth of 3. And then in example 2, we are given this tree where we have just a 1 and a 2, and we output 2 because the maximum depth here is from taking the path of node 1 to node 2, which has a depth of 2. So they give us a definition of a binary tree node up here, and we need to think about, so for this one we're going to want to use DFS to traverse the tree because we want to go depth first to find what the depth would be and then take the maximum of each of these depths. So first we're going to travel from 3 to 9 and get that total depth, which is 2. And then we're going to travel from 3 to 20 to 15 and get that length, which is 3. And then we're going to take the max, which is going to be 3 in this case. And then we're going to go from 3 to 20 to 7 and compare that to our other max, which was 3 so far. And they both have 3, so then we have 3, and that's the end of the tree. So we just return 3. So that's how that's going to work. And then we're first going to want to establish our base case, which is if our root is null, then we're just going to return 0. So, because then that has a depth of 0. Okay, and then we're going to want to use recursion to break this down into subproblems. So then we basically, on a basic level, we want the maximum for each subtree, right? Like let's pretend we have this example 2, just to make it more simple. So we technically take the max of the left subtree, which is 1 plus 0 because this node has a depth of 0, right? Because it's null, or the 1 and 2, which has a depth of 2. So max between 1 and 2 is 2. So then we're going to return 2. So the we're going to take the max of the left side, which is, so we'll call the method again with root.left, and we'll call the method again with root.right. And then for this, we're going to add 1 for each node. So, or for each call basically, because we're going to call it for every single node as we go down each path. So that's it for this one. It's a pretty simple one. And then the time complexity is going to be O of n, where n is the number of nodes in the tree. And that's because we are performing a DFS on where we have to visit every single node in the tree once to be able to find the max depth. And then our space complexity is O of n also, where n is the number of nodes in the tree. And that is because, so even though we don't see any data structures here, when you have recursion where you're doing DFS on a tree, then behind the scenes there's a stack that you're pushing all of the nodes onto as you visit them. And so because we visit every single node, so worst case, if we have something like example 2, they're not showing me the diagram anymore, but where it's just one line of nodes, right? And so every node only has either a left node or only has a right node, so the tree ends up being a straight line. Then we're going to have n nodes on the stack all at one time because that is one path, you know what I mean? But best case, if it's a balanced tree, so I guess kind of like example 1, but if node 9 had a left and right node, then it would be O of log n instead. That would be best case if it was a balanced tree. Because we would only have that many nodes on the stack at once. So it would be cut in half basically, you know what I mean? I don't know if I'm explaining it in the best way, but O of n is worst case, so we're going to go with O of n for space. So that's it for this problem. Thank you guys for watching, and let me know what I should do next. Bye.